Hi, my name is Travis Connor, and this is my Lab 2 motion of a falling object. For this lab, I observed the motion of an object dropped from rest, falling straight down. I decided to use a crumpled up piece of paper for my object because it's very light and is influenced by air resistance. I recorded this event and put the video in Tracker to be analyzed. I also made computational models to display this event. Overall, the purpose of this lab was to display the relationship between gravity, velocity, the effect of drag, and position in the y direction from an object falling. Here you can see a model displaying an object with only the force of gravity and a model with the force of gravity and drag. These models illustrate the forces acting on the two different computational models, which will be viewed later. The equations used in this experiment are also viewed here. The first equation used is to find velocity based on net force. The second equation is used to find distance traveled. The third equation shows that V average is equal to velocity final, meaning that the velocity equation can be used to find the distance. The next equation displays the force of gravity on an object, and the last equation displays the force of drag on an object. I use these equations in this lab because they allow me to find the velocity and position of my object while it is falling at any point. These equations also allow me to create a computational model of the situation. With this lab, I would find my computational model that included drag to be very similar to the real-life situation. In this experiment, the system was a crumpled up piece of paper, and the surroundings are the earth and air. The initial conditions for this experiment was my object at rest approximately 1 meter off the ground in the positive y direction. For the actual experiment, I took a crumpled up piece of paper and dropped it from 1 meter off the ground, as shown now. I then took the video and put it into Tracker, where I analyzed the motion of the paper. From Tracker, I could see that the change in the y position was not linear. This is because the force of gravity is in the negative y direction, causing the paper to accelerate as it moves downwards. I also coded a computational model of the situation. To start off, I made a model of an object falling only under the influence of gravity. The important aspects of the code that I changed from the starter code can be seen here. I changed the mass in line 36, the initial conditions of the paper in lines 39 and 40, and the time loop in line 65. I also added a line of code corresponding to the total force on the ball, as well as a line with acceleration in lines 66 and 67. I then used the acceleration line and updated velocity of the ball's line 75, and then I used the result of line 75 and line 77 to get the updated position of the ball. This model displayed an object falling with only the force of gravity acting upon it. Here are the results of the computational model with only the force of gravity can be seen. The position versus time is not linear, and the velocity versus time is increasing in the negative direction at a constant rate. The final distance of the object can be seen to be negative 1.07 meters. Next, I created a model of an object falling with gravity and drag. I edited the same lines of code as before, but this time I added a proportionality constant for drag force in line 56. I also added the force of drag to the total force equation in line 7. This allowed me to create a model that was almost exactly the same as my real-life situation that I plotted in Tracker. Here are the results of the computational model with gravity and drag can be seen. Similarly to the other computational model, the position versus time is not linear, and the velocity versus time is increasing in the negative direction at a constant rate. However, the final distance of the object is only negative 1.02 meters. Some similarities between my models and data were that the computational models with gravity and drag had the same final position as my data. Also, both computational models had very similar changes in position over time, as shown by the graph. However, as for differences, the model with only gravity fell further than my data. This was expected because without the influence of drag counteracting the force of gravity, the object can fall further. Also, my two computational models had linear velocity, while my data did not. This is also to be expected because the velocity is changing at a constant rate in the computational models and also in real life. But it is very difficult to plot that in Tracker due to discrepancies in data. One possible source of error could be my proportionality constant. I created a proportionality constant based on the equation shown, and it could be imperfect. Another source of error could be incorrect positions in Tracker, leading to incorrect data. The model of drag predicts the terminal velocity because as the velocity of the falling object increases, its drag increases while the force due to gravity stays the same, meaning that eventually after enough time the two forces will be equivalent and the terminal velocity will be reached. This can be seen by extending the time on the model of drag. If the object were thrown downward, the terminal velocity would be the same. It would just arrive at it faster. This is because terminal velocity is based on equal forces.